The Johns Hopkins Science Review, presented by Johns Hopkins and WAAM in Baltimore, in cooperation with the DuMont Television Network. Johns Hopkins has been famed for 77 years for its contributions to science and the humanities. Here in its many university and hospital laboratories, Hopkins scientists are constantly probing into the secrets of science, which, when solved, will be translated into benefits to be enjoyed by you. Each week, we look over the shoulders of today's scientists and catch a glimpse of the results of their research. On this, our 249th program, we bring you Concrete with Muscles. And now here to introduce this week's program is Lynn Poole.
Greetings, ladies and gentlemen, and welcome to another Johns Hopkins Science Review. You know, most people have said, I'm very much interested in how concrete is used to build things, but the science of it is too complicated for me to understand. Well, now, you don't have to be a mathematician or a physicist or an engineer to know how concrete is used. Because, well, with just matchboxes like this, things that you have around the house, and a simple rubber band, you can demonstrate pre-stressed concrete. And we'd like to try to make it just that simple for you this week. Well, now, here behind me, you can see on the campus of the Johns Hopkins University a typical construction job of our new engineering building, which is rising behind Gilman Hall. Now, you always see Gilman Hall on the opening of our Science Review. Now, in a very few weeks, this concrete in this building here will be completely covered by a brick wall. It will be covered to match the Georgian architecture of the Johns Hopkins campus. Now, that might explain to you, well, it might be hard for you to realize just how much concrete is used in our modern world. Why, it must run into the billions of tons, and most of it is hidden from sight. Now, more concrete is used than all other building materials put together, and probably no other building material has contributed so much to our modern civilization. Yet, most people wouldn't think of concrete as a chemical action. Strangely enough, an action which continues for years, a chemical action that continues after the concrete hardens and goes to work to hold up our buildings. In fact, the chemical action is going on right now in this block of concrete. This chemistry has been the subject of much scientific study which continues as new uses for concrete are developed. Now, when this chemistry going on here was better understood, there began in Europe some experimental applications of other scientific principles to concrete. Now, one was the principle of pre-stress, or actually squeezing the concrete. Now, our story of concrete begins with cement. Cement like I have here in this glass jar. Now, for this Science Review, we have asked Dr. Walter Boyer of the Civil Engineering Department of Johns Hopkins University to tell you more about concrete with muscles, or pre-stressed concrete. Dr. Boyer.
Thank you, Mr. Poole. Before we discuss how scientific principles have been applied to concrete in recent years, it might be a good idea to clear up, first of all, the meaning of concrete itself. It is a word which is often misused and misunderstood. You often hear the word cement used when concrete is what is meant. You have heard people say cement sidewalk, cement highway. There was even a popular song a few years ago about a cement mixer. These expressions are misleading because cement is only a part of the many types of concrete. You can see here that the cement itself is a very fine gray powder. This powder by itself has no power, yet when it is mixed with water, we form a paste which is one of the ingredients of concrete. So we have cement and water, and to this paste must be added aggregate. That is, sand which has been washed and processed, and also the coarse aggregate, which may be gravel from a stream, from a bank that has been processed, or actually blast furnace slag. These materials, when brought together, actually give us our material which we call concrete. In this block of concrete here, you will notice that the light portion up above represents the amount of cement that actually goes into making up this full mass of concrete. Another definition we should clear up at this time is the word Portland, which is applied to cement. This is by no means a trade name, as this product is produced by scores of separate companies, nor does it have any connection whatsoever with the 26 cities and towns in the United States which have the name Portland. It just happened that an English bricklayer perfected the formula in 1824 and named it after a natural stone quarried on the Isle of Portland on the south coast of England, as it resembled the natural formation found there in color. Today, this word Portland is used to describe a standard cement powder of known behavior. By using a standard formula, we can all benefit by the extensive research in concrete technology. As its findings are available to anyone, hundreds of research projects are constantly in progress in engineering colleges and in private and governmental agencies. The cement used today has been a standard product since 1917. The cement powder itself is an interesting material. It is really an example of man's taming nature and putting it to work to suit his needs. By sheer chance, nature created cements in limited quantities in certain places in the world. You here see a cement factory of ancient Rome, a volcano. Volcanic rock or sand found near Mount Vesuvius was used to make Roman concrete work, which still stands after some 2,000 years. The great dome of the Pantheon in Rome, 141 feet, both in diameter and height, still stands, cast in a gigantic mass of concrete. The foundations of the Roman Forum were a form of concrete placed to a depth of 12 feet. Even the famous Colosseum was built with stone and cement mortar. Many other of the famous Roman buildings which still stand use concrete construction, such as the Basilica of Constantine. We do not depend on volcanoes today to make our cement. The giant rotary kilns, some of them over 500 feet in length, do somewhat the same work, turning the clay and rock into cement at high temperature. The machinery in cement plants is almost as spectacular as a volcano, as it is some of the most massive moving machinery used in modern industry. But the great size of this machinery does not mean that cement making is not an exacting process. Literally mountains of rock, clay, and shale must go through some 80 different carefully and controlled operations until we finally have the resultant product, Portland cement. In effect, man reduces mountains to a powder so fine that it will easily pass through this silk scarf. Actually, a coarse test by comparison, since we usually use a screen of this type, a 200 mesh screen, which means 40,000 openings to the square inch. Water will hold on this surface if very carefully placed. In effect, we therefore have this very fine material, and many people never realize that this material can be used for home work as well as the very large applications that you see in your everyday life. Certainly, simple concrete work is no more difficult than many other household projects, and it's a valuable thing to know. Of course, the farmer has long known of its advantages and makes constant use of it.
The procedure of mixing concrete for large or small improvements around your home is much like that of baking a good cake. Good concrete, like good cake, is largely a matter of following a carefully tested recipe. The four ingredients of concrete, coarse aggregate, sand, gravel, or crushed stone, Portland cement, and water, must be carefully balanced and accurately measured for each type of job. No matter what you're planning to build with concrete, a sidewalk, an outdoor fireplace, or a flagstone terrace, your concrete must be accurately proportioned and mixed. And this is just as true when millions of cubic yards are mixed for, say, the Grand Coulee Dam. Suppose you plan to cast, for instance, the base for an outdoor fireplace. This is such a job in miniature. Just as for a cake of a certain texture, there's a specific formula for this concrete, established by many years of testing and experiment. When setting out to bake a cake, the housewife places everything she's going to need close at hand. You well know that an important part of it is correct measuring and utensils of the proper size. It's just the same in preparing to mix concrete. You should have pails, boxes, or other containers of known capacity, so you can be sure of your quantities. A sack of cement, by the way, is 1 cubic foot. Your measures can be related to this to make things easier. Now here's what your concrete recipe for this particular job would look like. A ratio of 1 to 2 1/4 to 3. This means a mixture which would look like this in miniature. We use a coffee can here as a standard measure. 1 part of cement to 2 1/4 parts of sand to 3 parts of gravel by volume. If a whole sack of cement were used, the 2 1/4 and 3 figures would simply mean cubic feet. I haven't mentioned the important water, which should be as clean as drinking water. If a whole sack of cement were used, this would work out to 5 gallons. Here, of course, this is scaled down proportionately to the correct amount for these small measures. And now, here in miniature is the mixing job. A trough of wood or metal is convenient, but it's not absolutely necessary. The cement and sand are mixed, the cook would say folded, to produce a mass of uniform color, with no streaks of brown or gray. Then, the measured aggregate is folded in until evenly distributed. And now, a hollow is made in the middle of the pile, and the water is added while the materials are folded. The mixing goes on until the cement, sand, and gravel have been thoroughly and uniformly combined. Within 30 minutes, the mixture goes into the form which has already been prepared in advance. Used motor oil can be used to lubricate it. It should be well tamped or spaded as it goes in to give you a smoother surface. And now you can say, your cake is in the oven. The freshly placed concrete must not be allowed to dry too quickly. This deserves as much attention as the correct time and temperature for your cake to be in the oven. The chemistry of concrete requires that the water stays in your concrete to properly harden it. If it evaporates, strength will be lost. So the new concrete should be protected from drying wind or sun for a week or 10 days. Flat surfaces can be covered with earth or straw, and the concrete kept moist by occasional sprinkling. This miniature example shows only one of 1,000 special uses for concrete, but it serves as an example to show that any kind of concrete mixing is not too difficult a job of planning, measuring, and mixing. In this way, you profit by all the experience and the years of research by the concrete experts.
Knowing how widely concrete is used, you might think that its advantages would be pretty obvious. You could readily see that it is durable, that it's clean, that it's fireproof, insect and vermin-proof. Its natural color is pleasant to the eye, but it may be colored or painted for decorative purposes, if desired. It cannot rust or rot. Moisture does not break down its strength. In fact, it actually improves it. Concrete can be mixed to suit a specific purpose. Both of these pieces of specimens that I have here are concrete specimens. Yet look what happens when I place them in the cylinder. As I place one in, it sinks. The other one is placed in, it floats. Concrete can be made such that its weight is 250 pounds per cubic foot. Or, like this floating concrete, it can be made so that it weighs 25 pounds per square foot. In other words, per cubic foot. Actually, just 1/10 the weight of the other. The floating concrete could be sawed or actually nailed like lumber. It also has remarkable heat insulating and sound absorption properties. Another advantage is what is known as precasting. It is now possible to build almost an entire structure of precast members of various types, made either on or near the job site, transported from a central precasting plant. Precise forms, often complicated and expensive, can be economically used to cast thousands of duplicate concrete pieces, which are quickly assembled when used for highway or railroad bridges. This method permits construction or replacement of an entire bridge in a matter of hours. Building the forms, casting, and curing the concrete can be done far in advance of actual construction, of course, and the savings in traffic delay and rerouting are large and important on crowded highways. Let me show you one more advantage of concrete which might not be so obvious as those I have spoken of. If you compare once again the amount of cement used in this concrete mass here, you notice that the lower portion represents the use of sand and aggregate, all local materials, materials that can be secured close to the job site, and these materials then processed and used with cement for the job. The cement itself probably did not travel very far to its destination, since plants are located in many parts of the United States and Canada. To the engineer and architect, concrete is an extremely strong material in compression. That is, to forces which tend to squeeze, compact, or crush it. Thus, the early uses of concrete were limited to foundations, walls, and other purposes where its great compressive strength could be utilized. We might have a brief lesson in bridge building to show you just what I mean. No one really knows who made the first bridge, but the chances are it was a tree fallen across some stream too deep to ford. It could not have taken long for primitive man to find out, undoubtedly the hard way, that a tree not only had to be of sufficient length to reach from bank to bank, but also had to have enough girth to support his weight. Otherwise, he was headed for a fall. Until a century ago, this fact hampered all designers of concrete structures. The reason is that while concrete is extremely strong in compression or crushing or pushing forces, it is relatively weak in tensile strength. That is, in the ability to resist being torn apart. These are the forces produced by loads on bridge girders and building beams and joists. Then around 1850, this problem was largely overcome by the development of reinforced concrete steel, which is a highly resistant material to tensile forces. This was embedded in concrete in the form of bars or wire mesh to form a material capable of safely carrying loads across long spans. But as spans became longer and loads heavier, engineers found that reinforced concrete, as all other structural materials, has its limitations. But again, what appeared to be a dead end has been bypassed. Today's builders have an answer to this problem in one of the most remarkable engineering advances since the development of reinforced concrete itself. Its name, pre-stressed concrete. It consists of ordinary concrete held under a permanent squeeze by wires or bars under tension as high as 225,000 pounds to the square inch. Thus we can say that to all of concrete's known advantages, we can now add muscles. Pre-stressed concrete is usually free from tension under normal load. The tensile forces are actually nullified, eliminated. To see how pre-stressing strengthens concrete, consider a bridge girdle. Under normal load, this member will actually bend so that the top portion is squeezed together or is in compression where the material is strong. The lower portion tends to stretch, is pulled apart, is placed in tension where the material is quite weak. Hence, we can use a reinforcing rod placed in the bottom to resist the tensile forces to give the material the tensile strength that plain concrete lacks. But pre-stressed concrete gets the same result in a more efficient way using steel wires, run lengthwise through a concrete girder and anchored at one end over here. At the other end, a powerful jack stretches them. Still under tension, they are firmly secured. The girder now has permanent built-in squeezing forces as indicated by these arrows, large enough to exceed any pulling force that will ever act on it. So a load can never subject the concrete to any tension at all. Plain concrete's low tensile strength no longer matters. You can apply the same principle by lifting a row of books all at once from a desk or shelf. If you apply enough pressure to the two ends of the books, This beam will actually support a load of one or more books placed on top of it. As you relax the compressive squeeze, tensile forces are produced, and there you see it. The great beam that you had before will collapse. Or you can actually feel pre-stressing. This can be shown by a very simple demonstration. Suppose we take a rubber band, hold it along the edge here, grasp it firmly in the palm, release the rubber band, and you can feel the squeezing forces on the hand. This is a same type of action that may occur in a pre-stressed concrete beam. Also, let me show another interesting demonstration that you saw before with the matchboxes. Suppose we place those up this way, then take a rubber band, place them around the boxes. They are brought together and form a beam which actually has the same form as a pre-stressed concrete beam. Of course, in this case, unlike the high-strength steel wire used in the concrete, the stress lasts only until the rubber band breaks. However, I'm sure that the rubber band can do its job a lot better than you can trying to hold up the row of books. Pre-stressed concrete has many unusual characteristics, among the most remarkable being its elasticity. Let me demonstrate that very simply. Consider this as a beam. Under load, even if it deforms, and it will deform under load, when the load is released, you will immediately see that the beam regains its shape, a property of pre-stressed concrete beams. I think this can be demonstrated very nicely by a model which I have over here. Notice in this particular model, the train's going backwards, that the bridge will actually sag quite a bit. This is not pre-stressed. Now, pre-stressing is on. Notice the rigid surge of the bridge. Now when the train goes over, there is very little deformation. Don't let this backward movement of the train annoy you too much. Backward operators are sometimes working on such a job. I would like to also point out that this backdrop behind me is quite an interesting one. It's quite fitting for such a program as this. This is an example of the first major bridge of pre-stressed concrete constructed in this country, the Walnut Lane Bridge in Philadelphia. A most interesting structure, 160 feet of sheer grace, truly a tribute to this type of structure. Now let me take you to one more very interesting demonstration. Over here you see three beams. One is made of plain concrete, one is a reinforced concrete beam, and the third one, the last beam in this line, is a pre-stressed concrete beam. I have weights here which weigh about 32 pounds each. Let's take one of these weights now and place it on the plain concrete beam. Well, you have an immediate failure from this load. This is not to be unexpected. Actually, as we mentioned before, plain concrete cannot resist tensile forces and will therefore break very readily. Notice, however, that the other two beams, one with a 1/4 inch reinforcing bar, the other with an 1/8 inch pre-stressed wire, actually carry loads well in excess of this. Three loads, about 100 pounds, being placed on the reinforced beam, 166 pounds on the pre-stressed beam. Yet the pre-stressed beam deflects less than the reinforced concrete beam. And wonderful demonstration of its capacity in this particular application. Pre-stressing reduces the bulk and weight of structural members. This method uses about half as much concrete and saves just about 75% of the steel. When ways to make slabs and beams by pre-stressed concrete have been developed for us, we find that they virtually open unlimited possibilities for us. Today it is being used to build houses, bridges, silos, water tanks, and many other applications. It provides a logical, economical answer to many engineering problems. You can look forward to longer, stronger, more graceful concrete structures than ever before, as this concrete with muscles of tomorrow is put to work today.
One of the uses of concrete that Dr. Boyer hasn't mentioned is that in the field of the fine arts. There are many statues and groups of statues around this country and other countries that are made of concrete. Now, course, concrete is only one of the many wonderful building materials that we have. Some of them steel, plastics, wood. All sorts of things are used to build the mighty buildings, the great bridges, and the wonderful things that you and I have today. And if you'd like to test the principle of pre-stressed concrete in your own home, you probably have some of these matches that we started out with this evening. If you have, go out in the kitchen and get a few boxes of them. Take a rubber band, put around them, and as Dr. Boyer said, you had a beam. And then, of course, you can have a lot of fun testing this by placing the matches across two surfaces like this. Then on top of it, place an object and see if it will hold that object up. As you see, this is slipped down a little bit. This is too heavy. But if I were to take the rubber band that I have here and twist it again, you see, I'm getting more strength to this beam, which I put on, and it stays very nicely. You can test pre-stress in your own home. We hope that you've enjoyed this presentation this week, and we very much hope that you'll be with us next week when the Johns Hopkins Science Review moves across the country, visits laboratories in other universities, as we see science coast to coast.
In laboratories and universities throughout the country, university scientists are seeking answers to unsolved questions of our universe. Next week, we will visit some of these laboratories and have a preview of some important developments in biology, in physics of the upper atmosphere, and a new interpretation of physical laws based on mathematical theories. These and other exciting new developments will be shown as we travel with Science Coast to Coast. The Johns Hopkins Science Review is produced by Lynn Poole in association with Robert Fenwick and John Lockwood. The directors are Kennard Kelpie and Herbert B. Cahan. Art direction by Barry Mansfield. Your narrator has been Ted Jaffe. The Johns Hopkins Science Review originates in the studios of WAAM in Baltimore.
This is the DuMont Television Network.